Well, let's try creating the vibrato equation now that we know that focusing our attention on phase is actually the most important design consideration. I'll begin by writing the sinusoidal oscillator as a constant amplitude A times sine of a phase function phi of t. And this phase function is what we need to properly design in order to obtain a correct implementation of vibrato. So a good starting point would be a constant ramp of slope 2 pi f naught. This would give us a constant valued frequency if that was the finished result for our phase function. Then to introduce vibrato, we need to cause a little bit of undulation or fluctuation about that ramp. And we can do that by adding a sinusoid to the ramp function. And that sinusoid should have a relatively low frequency, which normally we would call the vibrato rate. The variation makes most sense for the variation to be a sinusoid that is then superimposed or added to that ramp function. Therefore, our phase function phi of t can become the ramp function 2 pi f naught times t plus the frequency deviation delta f, which serves as a constant amplitude for our sinusoidal variation, which has frequency fr for the rate. So once we have the phase function in hand, we simply drop that into our sinusoidal oscillator equation. And we've got it. So this becomes the correct way of implementing the vibrato effect. Let's take a listen to this in LabVIEW. I have my delta F, that is my depth, and my modulating frequency. I have my tone frequency. Let's get the rate up there at a few hertz. All right, now we can start to perceive that vibrato effect. Take a quick rest there. All right, so simply exploring some parameter variations here. You'll notice that if you get much beyond 10 hertz, especially with a lot of depth, it doesn't really sound like vibrato any longer. So you really need to kind of keep the rate somewhere in the region of about 4 or 5 hertz or so.